just wait a moment until everybody gets in and gets their audio switched on. All right. Hello, everyone, and welcome to our Danish Sound Cluster webinar today. The topic is exploring the sound of Mars, and we are a little bit late because we have been struggling to fix our own audio settings. So we're going to work on that in the meantime. But today we have the whole space team from DPA, as well as the audio specialist who worked on the recordings, Eddie Brixen. And they are gonna talk you through the whole mission that happened in 2020. And please write your questions in the Q&A. We can just take them after the presentation. And we're recording the webinar today, so you can share it with colleagues or someone who might be interested afterwards. And if we do not manage to play the audio files for you now during the webinar, we will also make sure you get access to them later. So welcome. Thanks a lot for being here, everybody. I'll hand it over to Renee, who's going to moderate.
Yes. Thank you very much, Shelley, and thank you for joining in for this. I will be trying to share my screen, so hopefully you can now see something where it says DPA microphones, Mars 2020. And as Shelley said, we will not, we hope we'll be able to share the sound samples, etc. during the presentation. If not, we'll find a way to make that happen afterwards. Anyways, a quick tour of who we are today from DPA. It's myself. I'm René Mork. I have been with DPA for 7 years now as head of the product management, but I have also been previously with DPA back in 2006 and 2009 as an R&D manager. So I know DPA quite well. I don't have all the fine PhD and master in science. I know I'm only a bachelor in engineering and have an EBA. So that's my engineering background. But I'll just give you a quick tour of who the others are. So we have Tony, who is our technology manager. He's actually from Barcelona, but have been with us here in Denmark for quite a long time. And we have Rune, who is the design and innovation manager. He is very much focused also, of course, on our mechanical design. He will tell you a little bit about what some of the challenges we had on this mission. And last but not least, I think most of you will know Eddie Brixen, the guru or the master of audio in Denmark. If you don't know him, you should. That's all I will say about Eddie. So let's move on and get flying with this one. But before going into the details, I'll just tell you a little bit about who DPA are, because you may not know as much about what we actually do at DPA. So basically, when you think about a microphone, you think of something that you can hold in your hand and you can sing into it. That's basically what most people think of. So I started out saying, well, we are in live, and that's obviously both for some of the gentlemen and women you can see on this picture. Oh, I actually only chose men. That's quite annoying. Anyways, it's typically for singing, but it's definitely also for all the instruments, as you can see on Metallica's Lars Ulrich, almost hitting the microphone there on one of his toms. Moving on to some of the other things we are into, is the film. The film industry is very much depending on DPA microphones, our miniature, sub-miniature microphones. So, for example, the gentleman holding a statue from the Academy here, Mr. Simon Hayes. He is doing a lot of the A-grade films, you can say, including the James Bond movies and so on and so forth. He's very much using the DPAs, even on Bond's very, very small tie. It's actually hidden in there. Otherwise, they are somewhere on the body on Mission Impossible, they are even on the bike when Tom Cruise is riding that. Also, the shotguns are used there, so larger format microphones are used for that application. Last but not least, we also got some of our good colleagues got an Academy Award themselves for some of the mics that we do for the film industry. Next up is theater. That's really where we started out with the miniature mics. So whenever you go into the Broadway or West End in London, you will find DPA mics all over the place, and that's both on the characters, but definitely also in the orchestra pit. So that's a big part of seeing a show is the good dialogue, that you understand what is being said and being sung. We have some other areas that we also fit into, like broadcast. So when you see here in Denmark TV2 or Danish radio, you will see them wearing either as a lavalier or as a headset, as we're wearing here. You probably almost can't see it because it's only 3 millimeters. That's typically a DPA mic. We're also in parliaments. We're even some very, very fast cars. I can't name what it is, but they drive every Sunday. Again, it's reliability and the speech intelligibility, especially for the broadcast, that is the good thing about choosing a DPA mic. Well, going into working with NASA, that's quite special, obviously, and that's what we are obviously going to talk about today. But this is not the first time that we have been working with NASA. So we are a spin-off of the very well-known Danish company called Brüel & Kjær. And already back in the 70s, Brüel & Kjær were on the launch pads with NASA, and I know they also have other business with NASA. We have also, as in our own brand DPA, been working with NASA on the launch pads. So as you can see on the slide here with one of the space shuttles, again, because they can handle the high SPLs that are present when you send off a rocket like that. So again, it's not the first time, but this time it was a little bit like I say when we talk about what DPA is. Well, we make mics for the industry of entertainment. So this was really the purpose of DPA for this mission. That was to give people back home some good impression of what it will sound like when the rover enters the atmosphere of Mars, and hopefully also afterwards. But really, it's the entry that is on the agenda here. That was the purpose. So they wanted to have the images. They had 4 very, very high level cameras on the vehicle, and you've probably all seen the very, very good images coming from up there. But they also wanted to record audio. This is not the first time they had tried that. Last time it went wrong, so this time they wanted to put a little more energy into it. So our microphone is one of the 2s that are on board, and that's the one that should be working primarily on the EDL. And then they crossed their fingers and said, hopefully it also works afterwards. But as I have underwritten here, it's unlikely it will work beyond landing. And the reason for that is that they didn't go out and ask for special microphones here. They actually asked to use, or rather they found themselves, off-the-shelf components. So these are the 3 main components that we supplied. So it's one of our omni microphones, so it records everything around it, and it's a small amplifier. And as you can see, it actually holds a small, we call it the microdot connector. Some of you have probably been working with other microphones or even accelerometers, know about the microdot connector. And last but not least, our MMA-A, which is a A to D converter. So this little thing takes up to 2 microphones and digitize it into digital audio and send it out as either an iOS protocol or for this purpose an USB. So that was the three components. When they approached us the first time, I think this is back in 17 it was. And I visited them soon after. They had already bought a few mics and some of this stuff and other types of mics from us. I went into the office of the manager of this part of the mission, and he said, "Well, I already found a few things." And then he opened his locker, and in there was some of these components that you see here. And he simply used his Mastercard from JPL NASA to buy these things from whatever supplier that he found over there. So really, it was, as I say here, off-the-shelf components. So it was not something that was engineered from ground up to go on a mission to Mars. I remind you that's a long way to Mars. But I'll talk, or rather, our good friend Rune will talk a lot more about some of those challenges. So basically, it was the entry, descent, and landing stages or stage that we were to record and supply audio together with the awesome video that you have all seen from that mission. So it's really the 7 minutes of terror, as they call it. So obviously they're not sending live like a broadcast. There's a long way from Mars to here, so they don't know until it's actually landed safely, hopefully, on the surface of Mars, that you'll know whether it was or 20 minutes after, 11 minutes after, you'll know whether it actually happened and everything survived or not. And then you also have to have the data sent down. That's also a long way. It's not a fiber that you have up there. It really takes a long time to get the data down. And by that, I think I will first hand it over to Tony to talk about some of the things that we saw as issues entering such a hostile area as Mars, and even on the way up there, what will happen with the equipment we were to supply. So, Tony.
Thank you, René. Yeah, I must say, you just first contacts were already into 2017, but I didn't know anything about it. Suddenly, during Corona time, on a lockdown, it was a Friday afternoon that my boss called me, and he asked me, "I have a question for you, Tony. Hypothetically, if you landed on Mars and you put up a speaker and a microphone 1 meter far away, how would that sound?" I was, wow, that's quite a question for a Friday afternoon. Then my first thing was, okay, if we are hypothetically on Mars, then I can assume to start with that I can breathe, because otherwise it's going to be difficult. And then many other things popped up in my mind, and that's what I would like to explain a bit. What are the challenges for a microphone on Mars and also on the way to Mars? So if we move to the next slide.
Yes.
Yes, there are two critical moments for a microphone, at least. This is when we are getting out in space, and that's because we have atmospheric pressure on Earth around 101.3 kilopascals, and then we go to vacuum in just 90 seconds. That's really a huge change of atmospheric pressure for a microphone. And the other critical point is when we are landing, just the 7 minutes of terror that René was mentioning. We are traveling at 20,000 kilometers per hour, and then we have to land. And that happens in 7 minutes and 80 seconds after the entry in the atmosphere of Mars. We have a peak of heat in the heat shield that you have in the capsule protecting the rover. And there are around 1,300 degrees Celsius in front of the capsule. So that's quite some rough conditions. So will the microphone survive? Well, we have luckily a colleague, Jimmy, that could come up with a test. to evaluate how the pressure equalization, because the first thought would be, okay, should we adjust the capsule so that it can handle such a huge pressure change when we are leaving Earth and going into space? But then we could easily see that we would need to open the capsule, so the tube that is connecting the back volume with the outside of the capsule should be open that much that would actually destroy the low frequency response of the microphone. We wouldn't be able to capture sound at low frequency. So that was out of question. We want to record good sound on Mars. So then we had to prove that it could handle such a change of atmospheric pressure. And to do that, you can see the two pictures on the top of this slide, where on the right-hand side, you can see the capsule with a back volume connected to a pipe that is introducing, with a pump, that is introducing a 4.5 bar into the back volume of the membrane through the pressure equalization tube. And you can perhaps see in this picture that the membrane, which is very shiny, is bended upwards because there is a lot of pressure behind the membrane. And then we did that in cycles of 5 seconds on and off, just to see how the membrane would go up and down, but we were hoping that it wouldn't blow up the microphone or the membrane, and it could certainly tolerate it. So that gave us hope for or proof that this was a good capsule that could be sent to Mars. Yeah, let's move to the next slide. Then the next question is, okay, we can make it to Mars, but what will happen there? How will the microphone behave? What sound pressure levels can we expect during landing? And if it survives, what afterwards? And when you get to know, at least for me, that you get to collaborate in a way, in a direct way. I was just a consultant internally at DPA, but get to collaborate with NASA, then you want to do things very thoroughly and very precise. And one could think, okay, let's look at the Navier-Stokes equations, but after a few seconds, one can realize, okay, these are very tough, complicated equations that are complicated already on Earth. It's certainly more difficult to handle them on Mars. So let's try to be a bit more engineer, and could we prove that we can use the linear equations, acoustic equations, the wave equation, the Euler equation, and then in that way build simple models based on spherical waves to try to estimate what can happen on Mars. And to do that, you have here a condition at the middle of the slide that says that P, the acoustic pressure, in order to be able to use the linear equations, acoustic equations, you have to be sure that the acoustic pressure P is much lower than the product between the density of the medium where you want to propagate sound times the speed of sound squared. And that on Earth is a condition that we normally meet in almost every acoustical event that we can expect in a daily basis. So that's no problem, unless you go up to 140 dBs or really high or small cavities, holes, then it gets a bit more complicated. But normally in everyday life here on Earth, it's no problem. We can use linear acoustics for many things. But my first step was to see, okay, can we be sure that we can use this on Mars? And the first thing is looking at the atmospheric conditions. And the atmosphere of Mars is losing the gases that it has. And it's as a result of that, it means that it has a very low atmospheric pressure, around 610 pascals. And also that the density is very small. So you can see that if the pressure has to be smaller than the product of density and speed of sound, if the density is low, things are getting complicated. And then if we look at the sound, at the speed of sound on Mars, it can be shown that it's around 240 meters per second, which is also quite lower than the one we have on Earth, around 343 meters per second. And again, we have a problem, and the speed of sound on Mars is lower, not only because the density is much lower on Mars, but because we have another atmosphere that is filled with CO2. 90%, 95% of the atmosphere of Mars is CO2. And the elasticity of CO2 is really different compared to the elasticity of the air. And that affects also the speed of sound. Good. So we have some challenges. I did some calculations about that, and I could prove, or at least get an indication, that if we don't play that speaker that I was asked for to put on Mars, if I didn't play very, very loud, and I didn't annoy perhaps some extraterrestrial beings out there on Mars, then we should be fine and use the linear equations of acoustics. That was good. So how does it behave? If we move to the next slide, how will the microphone behave? We have tough atmospheric conditions, low atmospheric pressure, but especially the temperature. The temperature is changing a lot, quite often every day, from minus 140 degrees Celsius up to 20 degrees. This is hell for a microphone. I mean, the mechanical impact that it can have with such big temperature changes, it's really, really bad conditions for a microphone. But again, we try to be engineers and try to do things as simple as possible. If we try to estimate how this will change the sensitivity of the microphone, we say, okay, the thermal and the pressure coefficients of DPA 4006 at 250 hertz, at low frequencies, can be quantified on Earth. And these are quantified around some certain static conditions, reference conditions, and this is typically 25 degrees and 101 kilopascals, around that. And then what you do on Earth, you change these conditions slightly so that you can see how the sensitivity of the microphone changes in a smooth way. And then you can do a linear interpolation and estimate how much can sensitivity change per degree or per millibar or kilopascal. And you get these small coefficients that you can see in this slide. Good. Of course, here we are trying to estimate how the sensitivity will change from minus 140 degrees up to 20. So we are for sure probably beyond the linear approximations we are doing on Earth, but at least that's at least a quick estimate to get an idea of how the sensitivity of the microphone can change. And on the right-hand side, you have some simple calculations that show that at very low temperatures, around minus 140 degrees, we can expect that the sensitivity of the microphone will increase by 4.1 dBs. And if you go to 20 degrees, it will only change 0.1 dBs. And that makes sense because this microphone is designed to work on Earth, and 20 degrees is a much more comfortable normal temperature. So small changes for temperatures around 20 degrees, large changes at minus 140 degrees. And for the atmospheric pressure, you can see that we change around 2 dBs when we have atmospheric pressure of 610 pascals. It's an increase of sensitivity, and this is because these coefficients are negative. That means that the higher the temperature, the higher the atmospheric pressure, the sensitivity of the microphone will get reduced. So now on Mars, we have low atmospheric pressure, we have low temperature, so we have a tendency to increase, and that's what we expect, what we predict, that we have a tendency to increase the sensitivity of the microphone from 2.1 up to 6.1 dBs. That's what a simple calculation could prove. These are low frequencies where the response of the microphone is flat. If you go at high frequencies around the resonance, then the coefficients, the thermal and pressure coefficients can actually get quite nasty, quite difficult to predict, and change with frequency. And it can even turn from negative to positive. It's quite complex, but luckily here on Mars, we have an advantage, because if we move to the next slide, at high frequencies, we have another phenomenon that is not that frequent or not that important typically on Earth. And that is that because we have 90%, 95% of the atmosphere of Mars with CO2, we absorb a lot the air that is propagating, the sound that is propagating on Mars. Here, just to illustrate, on the left-hand side, we have the attenuation we can expect on Earth. And just for those that are not familiar with these pictures, we have on the y-axis, we have sound absorption expressed in dB per meter. So just to have an idea, the more meters, the longer the distance, the more dBs when you multiply with this correction. And on the x-axis, you have frequency, and you have really a broad frequency so that I can explain what are the different phenomena that happens. Typically, what you would have is that in air or in a gas, you can have three phenomena, if we simplify it. You can have absorption of sound because of molecular absorption, also molecular interaction. That is that sound waves travel through the molecules. These molecules get excited, and then will take energy from these sound waves, and they will start to vibrate. And depending on the molecules, and in this case on Earth, you have nitrogen, which around 100, 200 hertz start to absorb a bit of air. And higher frequencies at 10 kilohertz, it's the oxygen of the air that will start absorbing a bit of air. But these are small effects on Earth. I will come back to that. And at high frequencies, what happens typically is that you have thermal and viscous losses. That is that when sound waves travel through the molecules, this will start exchanging energy, heat, between them because the sound wave traveling through the molecules, and that would cause thermal losses for the propagation of sound. And it can happen that these molecules will start have friction between them, and then you will have viscous losses. Well, this is on Earth, and for instance, the nitrogen will create absorption at 200 hertz around 0.001 dB per meter, so insignificant. At 10 kilohertz, the oxygen will attenuate 0.2, 0.3 dB per meter. So this is a bit more noticeable, and at 20 kilohertz, it gets even more important. But in general, it's a small effect, unless you are looking into room acoustics or large propagation of sound. These effects are normally not taken into account when you are only measuring what's happening, the sound around the source at 1 meter, 2 meters. On Earth, it's typically not such a big problem. But on Mars, you have CO2. You have that it's already creating a lot of absorption, molecular absorption around 200 hertz. And you can see from this calculation that you already have 1 dB per meter at 200 hertz. So every meter that you travel for a sound wave at 200 hertz, it will get absorbed 1 dB. That's quite a lot. And at high frequencies, again, when it gets a bit more linear, you have a lot of thermal and viscous losses. And those will create a lot of attenuation. For instance, at 20 kilohertz, you would experience 10 dB of attenuation per meter. So just to, if we move to the next slide, what does this mean? If we now focus on the figure on the left-hand side, at the bottom, on Earth, we acousticians, we typically say, okay, if we have spherical waves, we have a decay of the amplitude of 6 dB every time that we double the distance that we propagate. So if we go from 1 meter to 2 meters, we will lose half of the amplitude of the wave. And if from 2 meters to 4 meters, we will lose again half of the amplitude. But you can see here the theoretical spherical propagation is the blue curve on the figure of the left-hand side. And as soon as you move up in frequencies, 100 hertz, 200 hertz, they are still quite close, the red and the yellow curve, quite close to the ideal spherical propagation on Mars. But if you move to 1 kilohertz, 10 kilohertz, and 20 kilohertz, then you can see you have a lot of attenuation. And at 20 kilohertz, you have already at 1 meter a deviation between the ideal spherical propagation and the 20 kilohertz curve of 10 dBs. At 2 meters, 20 dBs attenuation. So in conclusion, if you are on Mars, the high frequencies, they don't have a chance to propagate. And perhaps you have found on the internet videos explaining that the sound on Mars would be very low frequency. And it's not that you are boosting that much, at least not during propagation, you are not boosting the low frequencies. What happens is that the high frequencies disappear. And that's important because one of the questions we also had to address at DPA was, okay, what can we expect of sound pressure levels during the landing? And more particularly, how do we have to adjust the gain of the electronics so that we can record that sound properly and not create clipping effects? And then we could build a very simple model like the one you can see in this equation, where we say, okay, the output of the voltage will be related to the pressure of the jet generated by the jet. And this pressure here, if you can relate it to the x-axis on the figure of on the right-hand side, where you have the sound pressure generated by the jet at 20 centimeters. We try to estimate it here, and we try different values. What happens if it's 110 dB SPL, 120, 130, or 140, for instance? Then what can we expect at the microphone position, where here we simulated different distances, 1 meter, 1.25, 1 meter and a half from that jet. And then we played with different gains. And then we also accounted for the attenuation because of spherical waves, because the absorption of the atmosphere, the sensitivity of the microphone, the changes in temperature, changes in atmospheric pressure. So then we could tune the gain to understand where are the limits, the clipping points. And we came up with this conclusion you can see in this figure on the right-hand side, that around 125 dB SPL, we could reach the clipping point if we had a high gain, 30 dBs. And instead, if we set it down to 0 dBs, we could, in principle, record up to 150 dB SPL. So that helped us to adjust the gain of the electronics. That's very short, some of the things that we were working to understand how the microphone would perform on Mars. I give you the word back to René.
Thank you so much, Tony. Yeah, well, I'll just show you a picture here from from the assembly line, so to say, in California, because it's actually assembled at JPL in Pasadena. And to talk a little bit about some of the challenges that you have here. Hopefully, you can now see my mouse. Can you confirm that? Should have a yes, perfect. So this is basically this part that you see over here that you could look down on and have a good understanding of. And actually, back here is where you see the rover itself. It's lying upside down. Well, you have to have been there to understand that. I couldn't see it either. And just one mentioning here, all that we are sharing here is something that you can find on NASA's homepage, because obviously we're not allowed to release anything that is not official from NASA. But just to explain a little bit about some of the sort of disastrous things that Tony just mentioned, and Rune will talk about also, is the fact that it is coming in with a lot of velocity into the atmosphere of Mars. This heat shield will be shut off at a certain stage. The parachute will come out almost just beyond the surface. The last part, the crane here, they call it the descent stage, but it's also called a space crane. It has 6 thrusters, and those thrusters are obviously rockets. So that will give a lot of SPL. And our microphone is just next to it, but Rune will come back to that. And on top of that, that will be hoisted down then on the surface of Mars. So these are just incredible. An environment that is so hostile that it's beyond imagination. And of course, having no idea, or rather, Tony had an idea, as you could see, how it would affect the microphone and our ability to record it. But again, it was we were a bit scared about this challenge. But Rune, you can talk us through some of the challenges on the mechanical side that you had.
Thank you. Yeah, I was of course very excited the first time I heard that we were going to, or NASA reached out to us in respect to the possibility of sending a microphone to Mars. Yeah, and one day René dropped by and said that the NASA had a question, or asked us if we could come up with a suggestion on how to mount our microphone on the rover. And I was like, yeah, that's gonna be great. We're gonna come up with this super smart suspension system to separate or isolate any vibration from the microphone. It's gonna be great. And then René just looked at me and really sad and cold and sort of, we're gonna have no rubber and no springs. Oh, sorry, no rubber and no glue and no foam. Stuff that we would usually use to rubber to dampen any sort of isolation from the springs, foam to reduce wind speeds or sort of the noise from wind around it. We're like, okay, we're not going to use that. We're not allowed to do that because we don't want to contaminate Mars, so we're very selective on the materials that we could actually use. I was, of course, disappointed about that, because then, then we have to just mount the microphone directly on the rover with screws or something like that. So yeah, please give us a picture. Can you? Next slide, please.
Yeah, I'm trying.
Okay, fair enough.
There, got it.
Okay, yeah. So instead of a clever suspension system, we ended up on the left side of the rover. I think, yeah, that's much better. So coming from the standard microphone, instead of the suspension, we just send it on a diet. So looking at the microphone, sort of how much material could we remove from it. So I don't know if I can show. So originally the microphone looks something like this. And after the diet, it lost a bit of weight. So now it looks like that. So we removed any excess material, any excess surface treatment, anything that had any weight to it that we didn't need. Yeah, and also the way to mount it ended up being, we just bolted it to the rover. In order to do that, usually we have the preamp looking something like this. And there's a small ring here that you can sort of attach a suspension system to it. And that was removed. And then we, instead of just made some Mickey Mouse ears, I don't know here. So 2 holes and screw through that, and then bolted it to the rover. And that's kind of what we can, if we know what we're looking for, we can see it on the down to the left.
I can try to show it here. And over here. Yeah.
Yeah. So and that they made a sort of integrated system connecting the microphone directly to the PCB of the unit. This one. And again, sort of it was a little cloak and dagger from the beginning before we sort of knew that we had a solution. So creating the parts for NASA to try out. I just gathered some of the parts and went by the production site and asked one of our trusted employees could you please assemble this? Just imagine that it had the usual shape and just do what you usually do. And she of course did that. A few days later, we had the products and we could ship that to NASA. And it was first, again, I don't know, maybe a year later, was at least a way later that I could actually drop by her and tell her where the products that she had assembled, where they were ending up. And she was, of course, very excited about that. And we're allowed to be the one to assemble the parts that ended up on Mars. She had a lot of giggles on that. Oh, she was very pleased about that. And yeah, additionally, Tony talked a bit about the harsh environment. We, as a group, we looked at one another from time to time. Okay, well, what should we expect? Is there anything that we can do to help the success? And one of my concerns was, well, I heard that there were quite high wind speeds on Mars, and there's a lot of sand. So having a microphone with the membrane exposed, with the sand blasting, maybe not a good combination. So yeah, maybe I should just show more. Sorry about that. So yeah, we had the microphone, and I can just lift off the grid here, and this just you can see straight through it, and behind it will be the membrane. And we were concerned about that. So the suggestion was, okay, can we add in a very fine mesh behind the exterior grid to slow down the sand particles passing through the membrane to increase the likelihood of its survival. But again, mind you that we were not allowed to glue anything, so the design had to be lightweight and not excessive size, and it has to be sort of using the spring force of the mesh itself to get it sort of locked in place. So I actually had the pleasure to both make that small design tweak, but also to the assembly to fiddle the springs in place and do the final assembly of the microphone. So that was pretty cool. Unfortunately, they probably cleaned the parts before sending them to Mars, else I would have a fingerprint on Mars. Also, looking at the rover, you can see some wheels, and they were, of course, neither allowed to use rubber. So these are steel wheels with some suspension or springs through them, and we will come back to that later.
Cool. Perhaps I could add a few things also, because from the picture here, if you zoom in on that, I can't do that here, but that's actually a DSOP. So it's a military grade, obviously, DSOP. But as I showed you earlier on, the typical connector that we are using for some of our stuff is a microdot. And to my knowledge, the microdot was actually made for traveling in space back in the 50s, but they didn't want to use that. They used DSOPs. That's a bit odd. But anyways, that's you can see it's on a small metal bracket here, and then directly out of our unit, it goes into this assembly with the DSOP down here, together with some other stuff. A few more things I would like to add is that even though we all want to have electrical cars, this one couldn't carry a battery because there's no one up there to go charge it. There's no power banks you could plug into, so you would have to have some kind of source of energy, and I'm not quite sure it's called a nuclear power unit in here, but it's something that actually uses that form of energy, obviously, because it has to last a long time up there. And that means that there's some pumping of the liquid, just like in a cooler in a car, that pumps around the cooling from that engine, or from that power plant, if you like. And on top of that, it thereby also gives the electronics that's inside the rover a good and healthy life, because obviously there it's much more safe, so to say, both in terms of external environment, but definitely also in terms of the heating. You heard Tony tell about the big changes in the temperature up there. So as you can see, our unit is exposed on the outside, but the digitizer, the MMA-A, the one that is an A to D converter and a unit that sends out the USB communication, is actually in the stomach, so to say, of the unit. So that's much more well hidden in there, and lives a good life. Whereas those of you who works in electronics will know that making a cycle of 20 or even up to 50, I think, is the worst case, and down to minus 140 degrees Celsius is an absolutely nightmare. That's really how you try to kill things to see how long it will actually last. So that was cross fingers going out there, see what happens. But let's take you through the next stage, because the next stage of what is going on is that the rover has to travel from Pasadena. That's all actually all on a hill, and all the way over to Florida. You've all heard about Cape Canaveral, so that's where it's to be launched from. This is Dave Grew, who was in charge of this this whole thing, and I'm glad I was not in his shoes seeing that thing off, because I think it's $1.4 billion that has to go, first of all, down the hillside, and then next into this aircraft and flying it to Florida. Anyways, that went well, and it, as you can see it down here, now it stands just to be encapsulated into the rocket. That's in June 2020, and the launch was soon after. So it was, of course, as everything is, driven to the launch pad, and it was taking off on the July 28th. And of course, we held a small ceremony here in the cantina of DPA, and had a look at that on a live stream. Again, crossed our fingers, hoped everything went well and it didn't blow up on its way. And our marketing department made this little thing that's a regular 4006 blasting away, and yeah, as you know, everything went well, and it started its travel out there. So the next stage that where we actually have sound from, we also have some sound samples in between, but we cannot share that. But in October 2020, it actually entered, or it was flying out in space. And obviously there should be no sound out there. You just heard Tony tell about the molecules banging next to each other, and that's how the sound is propagating. So we're now in vacuum. So there should be no sound, but we were able to have some sound anyways, and that was also publicized. And Shelley, I'll try to push this and see what happens. Suppose you can't hear anything?
We cannot. We're in the vacuum. But I can share the audio file if you don't mind. Eddie said it's okay.
You can share it? Yeah, afterwards?
No, I can just throw it in.
You can do it now?
I can put it in the chat. So, of course, someone would have to open that on the other side. But if you want to listen, you can click on that and download it from the chat.
Perfect.
Yeah.
But that's you see also we put in the where you can find those files. But obviously, what happens here is that we are recording sound, a rather structural born noise from the rover, because at this point the power plant is engaged, and it wasn't engaged until it just prior to the launch. So that's some of the power plant stuff we talked about earlier on, and some of the pumping of the fluid that we're hearing at this stage. So moving on, now we are into February 18th of 2021, and this is all the fantastic images and the videos that we saw from up there. I was obviously sitting seeing this. We succeeded. That's this image. Obviously, we didn't have these images until later on, and that's what I'm gonna talk a little bit more into, and I'll hand over to Eddie in a few minutes, because that's really what we were there on board for. That was those 7 minutes of terror. So we were to record the entry, descent, and landing stage. So let's see what happened there. So on February in the weekend, it was landing on a Friday, and during the weekend we were supposed to have the files for cleanup and of course interpretations. And Eddie was on board of that on that part. So we heard the first sounds from Mars. Unfortunately, not from the EDL stage, because there was a software error. So there was no sound recorded from the EDL. But soon after, on the Saturday, they started it up again and had 60 seconds of sound, and that's what was then sent to us. Obviously, we got the file nothing in it. Was not that interesting. But then we got some actual sound. And Eddie, if you could take it from here.
Yes. Next slide, please.
Yes.
What we had was one file that we received for this purpose, and of course it was disappointing that the transmission system didn't work for the descent of the rover. But anyway, we got the first one, and it is what we got was a wave file because it was determined by the MMA. So in this case, 48 kilohertz, meaning we had full audio bandwidth with this one, and the resolution was 16-bit, and this provides us with a dynamic range of approximately 96 decibel. And it had 2 tracks, but it was mono. It was just the format by the MMA that by default provides 2 tracks. So that would be 2 identical tracks we had. And if you look at normally the format we use for wave files, we'll have a header with a lot of information. If you look at the header here, as you can see in the WinHex sheet, it doesn't say much. We can see at least it's a wave format, but a lot of the other information we normally would have in a header for a wave file is actually not present. So, but basically we knew what it was containing, this file. Next slide, please. So opening this file would contain some constant sound and something else. If we look into the constant sound, it is basically the baseline in these 2 waveform tracks, as you can see. There was some initial clicks that was from turning on, powering the MMA, the amp. And then you can see on a line, if I point with my cursor here, if that is possible, yeah. You can see there's something going on, and you can see that Sony had made a perfect calculation because there was not too much. There was still some good headroom. It's always a good idea to record with headroom. So I think that would be space enough for one of the jets if they should go off accidentally here. So that was actually perfect. But of course, when you listen to something in that level, you don't hear much until you amplify it. And there was this constant sound on it, and now I will do it in that way that I play back an audio file here, and you will hear it by my perfect microphone, I hope. So this is what it sounded like, and tell me not if you can hear it. Okay, that was what you basically could hear on that file. And as we don't think there were any Martians making that sound, it must be the rover that made it. So it would be nice to find out whether there would be other interesting thing on this recording. Can I have the next slide, please? Yeah, so here you can see it in 2 ways. That's both spectrogram and waveform in the same display in the isotope workstation. And what you can see in the low end here at the beginning of this file is that it has some low frequency content, because that's the low frequencies, and as it go in this direction for the 2 tracks, we get at higher frequencies. Also, you can see all the harmonics, individual harmonics that are just parallel lines all over the place, and that is the noise. And basically, this noise is from the power plant, the atomic power plant that pumps the fluids around to cool the thing down or keep more constant temperature. So that's related to the rover and not to Mars. And then, of course, you have, can I have the next slide, please? You have to consider, is that the thing we should present people with? I think people would be very disappointed anything they heard from Mars was just the engine you just put there. So it would be nice to perhaps take that away, and that's where the filtering comes into question here. I decided to make two versions. One, to be honest, and present the signal as it was recorded, just having some high pass filtering. You know, when we have a pressure microphone, it basically goes all the way down to DC, and that's why there is a vent or pressure equalizing tube built into it, so it can adjust for the pressure. But this vent, the size of this vent is normally for this microphone adjusted to 10 hertz, so it will record all the way down to 10 hertz. But as this should be listened to by people with normal listening gear or headphones and stuff, it was decided to make a high pass from 30 hertz. So everything that's going on between 30 and 10 hertz is not there. Then the other processing that was made here was trying to remove this power plant, taking this pump noise out of recording and see what the rest could be. So next slide, please. And whenever you are filtering sound in one way or another, you have to choose your weapons. There are a lot of possible signal processing out there. In this case, it was the isotope RX9 that was chosen for it, that was available at that time. Now it's the RX10 that is out there. But basically, it is a workstation that contains different plugins, and each plugin can be specialized for special kind of jobs. In this case, I after amplification, because I could use a little more signal before I did the cleaning, I chose a spectral denoise in adaptive mode. I did not need to go adaptive because it's rather constant, but I did that, but with a learning time of 1.5 seconds. And I had a noise reduction of 40 decibel in that case. And then I added the 30 hertz filtering after that. Yeah, you can go on to the next one. So here's one of the channels, and that is after removing the noise or reducing it by 40 decibel. And what you can see now is you have something here. It's very low frequency, and that's actually the wind. And then there are some chirps going on here, and that must come from the vehicle. I don't think ET is standing there calling home or anything. So it's his roaming from his Mars mobile that goes into our recording. It could be, but not in this case, I guess. So some chirps that is not related to the constant signal of the rover. And then we had the low frequency content, the wind actually. And based on the sound, whenever you have a microphone, any wind will create some noise, depending on what kind of microphone. The pressure microphone is a microphone that is least sensitive to wind, so that was actually a good choice for putting an Omni, a pressure microphone on this vehicle. But there is some sensitivity to wind, especially when it's not covered by anything, but only the grid. That is it. And if you do measurements of wind noise, you will also know that this noise increases with the speed of wind. So based on that, you could assume that this was a wind speed at around 5 meters per second, just based on the noise spectrum of this signal here. Anyway, I will try to play the wind here, and if you only listen on your oh sorry, I just have to open a file here, and here it comes. This is, I will play it again by my loudspeaker here, and perhaps you can hear some low frequency rumbling, because all this is actually taking place below 100 Hertz. But I'll give it a try. So here will be some rumbling going into my microphone. And here it comes. Yeah, that was it. I think it was difficult to hear, but afterwards you can go and hear the audio files that we provide, and also you can look it up at the DPA website on this thing. So you can see the noise is nicely removed, and we just have the wind and the chirps left. Next slide, please. Major Tom, thank you. Okay, so basically, I will not play it here, but you can go in and listen to it. But what I just played for you would be an original that you cannot hear much of because it's at a low level. And then there will be a version with which is amplified and has high pass filtering. And then in the end, the final version that we could say was related to Mars, basically, namely the amplified and with spectral denoise applied, and then some high pass filtering. So
Eddie, sorry to interrupt. I just shared it in the chat if anyone does want to play it.
Yeah,
the files
excellent.
3, 4, and 5, but we'll send it after as well.
Okay. But I've finished here, so back to Renee.
Perfect. Thank you, Eddie. Well, as we said, it survived both the travel from Earth, even from Pasadena, to Mars, the millions of miles up there, and it also survived the EDL. We heard the first sounds as Eddie just tried to share here. So thank you, Shelley, for sending that out on the chat. And last but not least, it actually survived quite a long time after, months and months after, which is quite amazing for a thing that is not made for traveling and going into such an harsh environment as on Mars. And Shelley, if you could also share this one, because that's really a fun part, because this is a recording. You would also find it on the NASA Mars homepage. This is a recording where it's the rover is driving, and they are recording some of that first driving on Mars. And really, what it sounds like is someone banging pots and pans, and that has something to do with the fact that Rune mentioned that there's no rubber wheels. It's well, again, they don't have a service technician up there to fix a punctured tire, so they put on these special alloy wheels, not the kind of alloy wheels you'll find on a supercar, but an alloy wheel that where the outskirt is really an alloy plate, and that is what we're hearing. We're hearing again some of the gears and some of the things that that is picked up by the structural noise, but we also hear the rover moving over the surface of Mars. And as Dave put on out in public, if that was my vehicle that sounded like that, I would immediately go into the roadside and ask for a tow and get it to the garage. So that's why I put in this picture of the garage, because that actually sounded very, very awful. So really nothing you would expect, but again, they were amazed by the fact that our microphone was surviving, and that they were able to record some of these things as well. So for us, it was also, wow, amazing that our electronics and our acoustics actually survives up there so long. And that's really boiling down to what we try to say at DPA. We want the clarity, and we want the consistency, and we want durability. If you can't see it, that's actually a heel on the last one, trying to smash one of our miniature mics. So yes, durability from off-the-shelf components. I think that's quite a statement. The last thing that we wanted to show here really is Dave Crew on the day of a press conference where they just received the files. I will ask you to go in and look at that again. The address is down here. You will be able to see him grab for the microphone, put that away, and start speaking into the Mars microphone. And in the end of this clip here, he is really emotional around the fact that they have audio from Mars. So yeah, for us it was also definitely a fantastic journey. It has been, and will continue to be. I'm sure I can say for all of us. So with that, we conclude what we had to present here. So I will not play these video files, and just ask you for any questions.
Thank you so much to all of you. That was a great presentation. There are a couple of questions in the chat. Would you like to take those? Would you like me to read them out, or can you?
Yeah, yes, please. That would be great.
Yes. So this is from Henning Larsen. What considerations have to be taken on the effect of vibrations during the active part of the recording? Are there directions of motion which are more troublesome than others?
Eddie, I think that's for you.
Actually, every microphone is sensitive to vibrations, and it's most sensitive in an axial direction, perpendicular to the membrane, to the diaphragm. That's it. But also all microphones are tested against vibration, so they will survive. In this case, it was most whether the most hesitating question would be, would it survive the vibrations and the vibrational levels that would be on this surface? And the second could be, what about the pickup of sound generated by vibrations? And actually, the noise maybe you heard. The noise that was in the file was actually basically coming from the structure-borne noise in the Rover. Considerations would be something like, will the microphone survive? That would be the most important. And I was not the one calculating that, but perhaps Rune can tell something about it. Did you calculate any vibrational levels?
No, we didn't.
Okay. So it just survived.
Yeah. Well, I remember you, Rune, saying that actually when you got the idea of how should we mount the microphone, you got excited and started to think all possible things. But then when you could see the requirements of NASA, that perhaps you can explain.
Yeah, that was what I said earlier, that sort of usually we would go into that and sort of, okay, how do we minimize vibration and transferred vibration, so noise from a moving vehicle or from clothes or motion of a person, and we do that in a few different ways, but sort of all the usual tricks that we would pull out of the box for sort of, oh, we can't do that, we can't do that, we can't do that. Well, okay, then sort of all the good stuff are not allowed. So okay, so we're gonna just do the basic stuff and ensure that at least it comes down to us in one piece, and let's cross our fingers for that it still works.
I can read from the specification that the Influence from vibration is 64 decibel equivalent sound pressure level for 1 meter per second squared of acceleration. So yeah, that provides some sensitivity, but not so much.
We have a few other questions here. From Daniel, do you see a possibility to send more microphones in future lander missions?
I think actually that part of this having audio has really made I think not just NASA but also other organizations think about how to utilize microphones in the future for audio recordings, because it has given them a lot of insights. Also in the aspect of actually going there with human beings, they got some eye opening because again, as Tony showed, he did a lot of calculations of what could we expect, and of course they did so too. But they actually got pretty surprised about how it actually sounded up there. So there's a lot of learnings around having audio from outer space. I think I can say from DPA, it's not a market segment that we're going after. There's only that many organizations doing that sort, but it has been an absolutely pleasure to work with NASA on this mission.
Okay, and
if I may supply
go ahead.
just one comment from my personal side of here working and trying to design microphones. When thinking about the properties of sound on Mars, I think it could be very cool if we could look into that for directional microphones, because we designed them on Earth, and I have an idea that they would perform quite differently on Mars, just because you have such amount of attenuation, and that would affect a lot the adjustments we do between the front and the back part of the microphone for directional microphones, and also the fact that you have other molecules than air inside the capsule that would change the acoustical properties inside. So it would be a suggestion for you, Rene, for NASA next time you talk to them. Why don't we send a directional microphone up there?
Okay, and then we have a question from AH. How would you have rigged up microphones on the rover if you'd have fewer limits on weight and how many different mics? Some kind of array. Don't know who that question's for.
Yeah. Well, I think Rune sort of talked into that a little bit about all the suspensions and all the protection mechanisms that we would have loved to put in there. But again, mind you that we were just for the entertainment part, is not for the scientific part. So this was really for the EDL stage. So seen from our point of view, as it was pointed out, a pressure microphone was not that a bad choice, because it is less sensitive to vibrations and to the wind noise and so on. But of course, we would have loved to seen a lot more mics on it, and as Tony states, it would have been awesome to have a directional mic up there as well. But yeah, you can only dream.
But having a stereo pair or surround setup or something would be
cool. I cannot comment on that. But yeah,
that would be nice to be fully immersed in the Martian wind. Yes.
If you think about this, the immersion of sound, it must be complete. If we could breathe and have the head outside, it must be completely different. I mean, sound is attenuating a lot of high frequencies, so also when we get away from one side and it will pop up at the other side, our perception of sound should be different. In that, and the speed is also slower, so sound also takes longer time to reach you, and all those things. So the sound perception must be really different if we can breathe.
I was wondering, this might be a stupid question, but do you know what kind of audio configuration the astronauts are using in their spacesuits to communicate with one another?
I know of a company, I cannot say who it is, that actually uses ours. But in general, no, I don't. I'm not aware. Perhaps some of the others joining in for this knows that.
From the audience, you mean?
Yeah, from the audience, exactly.
Anyone out there? It's not something you're doing every day, but oh, okay. We have a question from Elizabeth. What about durability in such a hostile environment? Is the microphone still working? If yes, do you know how long it will last before the dust affects its performance? About 2 months, was it?
To my knowledge, it doesn't work anymore. But it did work for quite a long time, for months and months, which is amazing, because typically what you do from an engineering point of view, obviously, you actually cycle in temperature to find malfunctions in both your electronics and your mechanics and acoustics, as mentioned. So living that long up there and having traveled millions of miles is absolutely amazing for off-the-shelf components, not made for this. I remember when I went to I'm from Aarhus. There's a company over there also doing stuff for space applications. And one of my teachers at I was in Danish Ingeniørhøjskolen in Aarhus was working for this company, and he always told us when we designed amplifiers and power supplies, oh, you must remember that it should be able to go into space. I said, well, yeah, not for me. I will not go there. That's not where I'm heading. I'm in audio. I will be in audio. But well, all of a sudden we were there. We didn't intend to do this for that application, but apparently we're quite good at what we're doing, because the electronics really did survive this very, very hostile environment and journey.
Yeah, it's really impressive. Well, congratulations to everyone at DPA and Eddie as well. Yeah, I think we're approaching the end of our time now. So if there aren't any more questions from the audience, we will.
One more.
Yeah. Oh, sorry, there's one in here. Can we be sure that some of the recorded sound is actually airborne, since it all comes from wind noise, which could be the vortices hitting the diaphragm directly, and the robot itself, which can be transmitted through vibrations?
We are definitely sure that that the sound from the vehicle driving is acoustical, and I think Eddie, you can also say that that the wind gust that we hear from up there is also from an acoustical recording.
Because how do you know that?
Eddie, that's a cue for you, I guess.
Any microphone in a windy environment generates sound, and sometimes it's the surroundings that's activated by the wind. Sometimes it's a membrane activated by the wind itself, and basically it's a movement in the membrane, and that's what the transducer is there for. So I guess what we heard here was basically most of all, and based on the spectrum of it, it would be the wind generating the sound by moving the membrane in this case. But that's an sound engineer's problem when he's doing recording. He doesn't want the wind, but he likes the sound that the wind makes in the environment. And sometimes it can be difficult to get them separated. And that's basically the same thing that happens here.
All right, thanks for your answer. Well, then I think we might be finished for today, unless anyone has any final comments. Not from you guys. All right. Well, thanks for joining. We have a few other interesting webinars that might be of interest to this audience. One next week about sound in robotics, and then we have tuning live sound at Roskilde Festival the following week. And we also have a very fun innovation partner event at Roskilde Festival, where you actually get to go to the festival on the 26th of June. So please keep an eye out for our newsletters and sign up for those other events that might be interesting for you. And yeah, we'll send out the presentation and the audio files if you didn't get them. So thank you very much, everyone, for attending, and thank you to Tony, Wona, René, and Eddie for joining today and presenting.
Thank
My
you.
pleasure.
Thank you.
Thanks a lot. Bye.
Bye bye.
Bye.